Hello friends, in the last lecture we have learned about real lattice and reciprocal lattice. In this lecture we are going to discuss about a related topic, X-ray diffraction. Students of material science and engineering are familiar with Bragg's law of X-ray diffraction. However, in this lecture I am going to talk about von Laue condition of X-ray diffraction. You are shining X-rays on the material. So the incoming X-rays are coming in this direction of n hat. And each atom or ion arranged in a Bravais lattice, they are re-radiating the incident radiation in all possible directions. Let us take one of them, right? So let us assume that the incoming wave, the incoming radiation is in the direction of n hat, and the outgoing radiation is in the direction of n hat dash, right? So these are the like two unit vectors in those two directions. Okay, we have to find the condition for constructive interference. Let us take two atoms separated by a distance of d. So we have like atom 1 and atom 2, and they are separated by a distance of d. Now we define the wave vector k. Correct. So this is the wave vector of the incoming wave, right? K is the wave vector of the incoming wave, right? So we take the magnitude that is equal to 2 pi by lambda times its direction n hat, and k dashed is the magnitude of the or k dashed is related to the wave that is going in this direction, and then again its magnitude is like 2 pi by lambda times its direction is n dash. Okay, note that because of elastic scattering, both the both k and k dash, both of them has same wavelength. Now again we know that this d is the separation between these two atoms. So what we do is that now we calculate the projection of d along k. Okay, so to do that, what we have to take a dot product, right? So d dot n hat is the unit vector along k. So this will give the projection of d along k. Similarly, we can get the projection of d along k dashed, which is given by minus d dot n hat dashed. Now you see that these two waves, right? The first wave that is coming in this direction, and then this is like going out in this direction. Similarly, if you look at this wave, right? So this is the incoming and this is the outgoing, right? So if you compare these two waves, right? This and then this, then you see that this wave, right? This particular wave is traveling more path than the second one. And then what we can do is that we can just find out the path difference between this and between this. How do we do that? The path difference, and you see that the extra path that this wave is traveling is given by this plus this, right? So this is the extra path that is being traveled by this wave, right? And we already have found out right what that is, right? That is just the projection of d along this, correct? And then we can just add these two terms to get the path difference, and that is given by this equation. Now what is the condition for the constructive interference between these two waves? The path difference should be equal to some integer times the wavelength. Okay, and then what we do is that we take this equation and multiply both sides by 2 pi by lambda, and then we can rewrite the equation as this, right? So d dot k minus k dashed is equals to 2 pi m. So this is the condition for constructive interference. Now you see that d is the distance between these 2 points, right? Any vector that takes me from one lattice point to the other lattice point is a lattice vector, right? So d is some lattice vector, but now we can generalize, right? And then we can just put in place of d, we can just write it as r, right? Because this must be true for all lattice points, right? So d is replaced by r in this equation, and then we just write it as r dot k minus k dash is equals to 2 pi m. And then if we just take exponential, right? So e power this is equals to e power I 2 pi m, right? But now 2 pi m, right? So this is like m is an integer, right? So that must be equal to 1. So that means we can get this equation. Okay, e power I k minus k dash dot r is equals to 1. Now we compare this with what we already know, right? We have already derived this, right? E power I g dot r is equals to 1. Correct. So if we compare these two equations, then we can just conclude that k minus k dash, that is equal to delta k, that must be equal to g, where g is some reciprocal lattice vector, and this is known as the Laue condition for diffraction. So we can take the Laue condition, delta k is equals to k minus k dash equal to g, and represent it in a diagram. So we can just rewrite this equation as g plus k dash, right? So we just use the vector sum rule. So this is like g plus k dash is equals to k, right? This is the k vector. And then you see that the magnitude of k dash and magnitude of k, they are same, as the scattering does not change the wavelength, right? These are like elastic scatterings. So in that case, what we can write is that we can take this equation, right, and just square it. Correct? So if we just square this equation, what we get is the following, right? K square is equals to k dashed square, right? So this is what we are saying, right? The scattering does not change the wavelength, so their magnitude must be same. So we are just taking square of the magnitude, and then what we do is that we just rewrite this equation, right? So this is equal to, correct? This is equal to k square. Correct. What is k dash? K dash is k minus g, right? So this is like k square minus 2 k dot g plus g square. Okay, and this implies that we can just write this, right? K dot g, right? So this is like k dot g is equals to half of, so this term cancels out from both the sides, so this is half of g square. Correct. And then what we do is that we can just rewrite this equation. So we just divide this vector g by its magnitude, so that we can just rewrite it as k dot g hat is equals to half of magnitude of g. Okay, so this is what, so Laue condition, we can just rewrite this as this. Laue condition is given by this, right? We can just rewrite, we are just rewriting this equation like this. Now if you look at this diagram, then you see that this component of the incident wave vector k along reciprocal lattice vector g, right, that is given by this, right? So k dot g hat, what is this? This is the component of the incident wave vector k along the reciprocal lattice vector g. Okay, and that is equal to half the length of g. So that is what we conclude from this equation, right? And then if you look at this diagram carefully, then you see that the tip of k is equidistance from O and the tip of G, right? So this is the tip of K. So this is equidistance from O. So this is this O point, right? Some point in reciprocal space. And then this is the G point, and the tip of K is equidistance from both the these points like O and G. So that means if we draw a plane, right? You see this blue plane, right? If we draw a plane which is like perpendicularly bisecting the line joining O and G, right? Then what will happen? The tip of this vector k will lie on that plane. Okay, and this plane has a special name. Such perpendicular bisector planes of G vectors in K space, these are known as the Bragg planes. Let us draw the perpendicular bisectors in case of 2D. We can do it in real lattice as well as reciprocal lattice. For example, let me show the example for a hexagonal lattice. Okay, so these are the so this is one vector, right? A1, correct? and this is joining like two real lattice points, correct? This and this, correct? So what we do is that we just draw this perpendicular bisector, correct? And this we are doing in the real space. And then we can again take this point and right, and then we join them with a line and draw the perpendicular bisector, right, which is this. And we can do it again for this point, and then we get another perpendicular bisector, which is given by this, and so on, right? And then you see that this is how so then you see that we have like built a small cell, correct, within this, right? Small cell which has the boundaries are given by these red lines, correct? We have built a small cell by joining the perpendicular bisectors. In case of real lattice, these are known as the Wigner-Seitz cell. Now, this is the corresponding reciprocal lattice for the hexagonal lattice. And then these are the vectors, right? B1 and B2. And then you see that you take 2 points in the reciprocal lattice, and then you draw the perpendicular bisector, right? And you do the same thing, right? Again, you take these 2 lattice points and you draw this perpendicular bisector, correct? This one, correct? And then you do again the same thing, and then you see that again you build a small cell inside, and then right, this cell is known as the Brillouin zone, right? So the principle is same. You just join you just draw the perpendicular bisectors, and that will give you a cell. Either in real lattice or in reciprocal lattice, and this cell has a name in case of real lattice, this cell, right? Maybe I can just right, so this is the cell that I am talking about. This is known as the Wigner-Seitz cell in case of real lattice, and if you look at the reciprocal lattice, then this is the cell, correct? And then this is known as the Brillouin zone. You notice like if you look at these figures, you notice one interesting thing is that this Wigner-Seitz cell and Brillouin zone, they are rotated by 90 degrees with respect to each other, okay? And now you see this, the boundaries of the Brillouin zone, right? We just have read about like Bragg planes in the previous slide. We just have learned about that. And then you see that these boundaries of the Brillouin zones, these are the Bragg planes. Finally, let me just summarize the most important concepts in this lecture. So we have defined like 3 basis vectors for real lattice or Bravais lattice, and based on them we have defined 3 basis vectors for the reciprocal lattice, okay? And then we can write a general vector in reciprocal lattice in this form, and these G vectors, these are like special wave vectors such that the plane wave e power I G dot R has the periodicity of the real or direct lattice. Now we also learned about Laue condition for this diffraction, and they can be represented in 2 different forms, right? So delta K is equals to G, or K dot G hat is equals to half of G, okay, where G is a reciprocal lattice vector and K is some general wave vector, okay? And then what we did is that we defined like perpendicular bisector planes of G vectors, and they have a name, like they are the Bragg planes. And then we have also defined something called Brillouin zones, and then these Brillouin zones are the boundaries of the Brillouin zone, they are the Bragg planes, okay? Why did we learn about this Brillouin zone and Bragg planes? Because they will play some important role when we try to understand the electron in a periodic potential. After learning the concept of real and reciprocal lattice, let us get back to our discussion on electronic properties of solids. We have discussed free electron theory in great detail and realized that there are certain anomalies which cannot be explained even at the level of quantum theory. Thus, we decided to include electron-ion interaction. Our discussion on lattice also taught us that the Atomic cores or ions are periodically repeated in space. We have to solve time-independent Schrodinger equation by taking into account the periodic potential because of the underlying lattice. This will not only help us to understand the electronic properties of semiconductors and insulators, but also explain the sign anomaly of Hall coefficient of divalent and trivalent metals. We shall start our discussion with Bloch theorem. Before we do that, let us have a feeling that how does a periodic potential look like. A schematic diagram of a periodic potential is shown here. Blue points are lattice points and the red line is value of potential energy which changes periodically in space. The lattice points are arranged in a distance of a. Starting from a lattice point, you can reach another lattice point by moving by a vector r, where r is equals to n times a. N is an integer. For example, to move from the first lattice point to the second lattice point, you have to move by a vector r equal to a. Similarly, to go from the first lattice point to the third lattice point, you have to move by a vector r equal to 2a. The potential is periodic, that is u of r plus r is equals to u of small r, where small r is some general point and capital R is some lattice point or lattice translation vector. So what does this imply? This implies that if I am, say, at this point, which is not a lattice point, and then I move by a lattice translation vector A and reach at this point, and the potential at this point and this point must be equal because of the periodic nature of the potential. Remember that valence electrons get detached from the atomic core, which is made of nucleus and core electrons. Since the atomic cores are positively charged, close to the cores, the valence electrons see some highly attractive potential. As it moves away from the core, the attraction gets weaker. We have to solve time-independent Schrodinger equation for a periodic potential u of r. We have some experience of solving time-independent Schrodinger equation for some given potential like harmonic potential. But solving for periodic potential is more complicated than solving for a harmonic potential. For solving time-independent Schrodinger equation in periodic potential, we need to learn Bloch theorem. This theorem is so important that electrons in a periodic potential is referred to as Bloch electron. I shall not try to prove the theorem, but just explain its consequences. Let us try to memorize Bloch theorem by starting from something we already know, that is the wave function for free electrons given by e power I k dot r, where k is some wave vector and r is some general point in space. Wave function for Bloch electrons is given by the wave function for free electrons multiplied by u of r, where u has the periodicity of the Bravais lattice. That is u of small r plus capital R is equals to u of r, where capital R is some point in the Bravais lattice. Let us try to calculate psi of r plus capital R. This is equal to e power I k dot r plus capital R times u of small r plus capital R. We can rewrite this as and since this has the periodicity of the Bravais lattice, we can write it in this form. And note that this is nothing but psi of r. Thus, psi of r plus capital R is equals to e power I k dot r times psi of r. where capital R is some Bravais lattice vector. Now, we can restate the Bloch theorem like this, and let us use this form to understand the meaning of Bloch theorem. Let psi of R be the wave function at some point R in a crystal. Now, let us move by a Bravais lattice vector R from the above point R. Now, what is the relation between the wave function at small r and small r plus capital R? Are they equal or not? Or alternately, you can ask the question whether the wave function also has the periodicity of the Bravais lattice, because if psi of small r is equals to psi of small r plus capital R, then we have to conclude that the wave function has the periodicity of the Bravais lattice. Clearly, that is not the case, because the wave function at R and small r plus capital R differ by a phase factor of e power I k dot R. Thus, the wave function does not have the periodicity of the Bravais lattice. However, you try to calculate the mod square. This is equal to e power minus I k dot R psi star R e power I k dot R psi of R, and this term cancels out, and we can write it as psi of R square. Thus, we find that although the wave function does not have the periodicity of the Bravais lattice, but the probability density that has the periodicity of the Bravais lattice, because psi of R square is equals to mod psi of R plus R square. Let us try to understand the significance of K for Bloch electrons. Wave vector K of Bloch electrons are similar to the wave vector K of free electrons, but there is a difference. We know that the plane waves are eigenstates of momentum operator with eigenvalue h bar k. However, Bloch states are not eigenstates of momentum operator. This is very easy to verify. So, Bloch states are given by psi of R is equals to e power I k dot R times u of R. Now, I write the momentum operator in 3D minus I h cross times the gradient operator, and then this operates on R. And this can be written as h bar k e power I k dot R u of R, and now I take a derivative of u of R, so e power I k dot R gradient of u. Clearly, psi of R is not an eigenfunction or eigenstate of the momentum operator. Now, a term is used showing the similarity but also highlighting the difference. For free electrons, we know that the h bar k is the momentum eigenvalue. For Bloch electrons, h bar k is not the momentum eigenvalue, but we use a term which sounds familiar or which sounds similar, and that term is the crystal momentum. We will see later that dynamics of Bloch and free electrons differ in general. In case of free electrons, the velocity is given by h bar k divided by m. H bar k is the momentum divided by mass, and you get the velocity. However, velocity for Bloch electrons given by v is equals to 1 by h bar del E del k. We solved the problem of free electrons in a periodic box of volume V. Let us now try to do the same for Bloch electrons in a periodic box. In case of Bloch electrons, the big box of volume V is made of small unit cells representing the underlying lattice. The volume of the big box V is given by the number of unit cells present in that box times volume of each unit cell, that is n times V. If you look at the periodic boundary condition, then it looks same for the free electron as well as Bloch electrons. However, one should keep in mind in case of Bloch electrons that we have to consider two length scales. One is macroscopic length scale and another is atomic length scale. The macroscopic length scale is given by the length of the side of the big box L1, and the atomic length scale is given by the lattice translation vector A1. So that is where the Bloch electrons differ from free electrons, because in case of free electrons, we only consider the macroscopic length scale and completely ignored the atomic length scale. Let us find out the allowed values of Bloch wave vector k. In case of free electrons, allowed values of k are determined by periodic boundary condition. This is true even for the Bloch electrons. However, in case of Bloch electrons, they must also satisfy Bloch theorem. Now, let us take the periodic boundary condition along the direction of vector A1. So, according to Bloch theorem, we know that psi of r plus r is equals to e power I k dot r psi of r. Now, in this case, r is equals to n1 times a1. Thus, we can write psi of r plus na in this form. Now, we write the wave vector k as a linear combination of b1, b2 and b3, the vectors in the reciprocal lattice. Here x1, x2, x3 are real numbers. Now we also know that ai dot bj is equals to 2 pi delta ij. That means when I try to calculate this term k dot a1, the only term that will be non-zero is b1 dot a1. Rest of the terms will be equal to 0 because b2 dot a1 equal to 0 and b3 dot a1 equal to 0. Thus, we can write psi r plus na is equals to e power I n1 2 pi x1 times psi of r. But according to periodic boundary condition, psi of r plus n1 a1 must be equal to psi of r. And then you can compare this equation and this equation, and the only way it can satisfy both of them is if e power I n1 2 pi x1 is equals to 1. And then we can write x1 as small n1 divided by capital N1. And similarly, we can find the value of x2 and we can find the value of x3, and then we can write the wave vector as k is equals to small n1 divided by capital N1 b1 plus small n2 divided by capital N2 b2 plus small n3 by capital N3 b3. From this equation, we can also find the volume occupied by a k point, and that is given by this. So this is nothing but the volume of the primitive cell of the reciprocal lattice divided by the number of the unit cells. And if you calculate this number turns out to be 8 pi cube divided by V, which is same as what we found for the free electrons. However, keep in mind that in case of free electrons, we did not talk about reciprocal lattice.